Hello everybody, so today we're going to be covering sigma notation, and this is what sigma notation looks like. So today you'll be seeing what this fancy little thing does in mathematics, more specifically in calculus, and why do we need it. Okay. So in the previous videos, we mentioned that integration is the inverse of differentiation, and this is the notation for integration. This is the notation for derivatives. All right, and here's an example. Let f of x be a function cosine square of x plus 3x squared. Let's find the integral. Let's find the antiderivative of that function. All right, for that we use the symbol for f of x. Let's take the integral of that. Let's take the integral of the other side as well, and we can see that one of the properties of cosine square of x is that we can bring the 2 to the front. So then we have the integral of little f of x with respect to x is equal to capital F of x, and this 2 serves as a constant. All right, so we can actually bring it outside, and we have that this is equal to 2 times the integral of cosine squared with respect to x, plus, remember that was one of the properties that we can split sums, 3, which is also a constant, times the integral of x squared with respect to x. If we carry that operation, we have that this is equal to 2 times the antiderivative of cosine of x is sine of x. Let's see, that derivative of sine is cosine. Yes, that works out. So plus this 3 stays here. Let's undo the power rule on the x squared. X to the third power over 3 plus this constant of integration. If we put everything together, we have the capital F of x is equal to 2 sine of x plus x cubed plus our constant of integration. And remember that this final formula is what we call the general solution, right? We do have this capital f of x equals this function with a constant here. We do not know what the value of the constant is. If we want to know what the value of the constant is, then we are required to be given a initial condition, all right? And then we can find the particular solution, and the particular solution will be given using this value of C. Another interpretation of integration that we're going to be using in this course is finding the area under a certain line. And let's remember, lines are not just straight lines, there are also curvy lines. So we just say, let's find the area under a curve, all right? So in the first example, if we are given to find the area under this curve, well, this seems fairly easy. It looks like a triangle. We do know a formula for a triangle, ta-da, we can do it. But if we are given something more like this, how do we find the area of that? Well, we are going to be learning some techniques in which we partition the area under a curve into small sections, and then each of these sections we can find the area, and then we add all the small areas and obtain the entire area. Each small part is integral to forming the whole area under the curve. That's also where the name integration comes from. All right, each area is integral to the area of the entire region. Ta-da! But before we start doing any of that crazy amazing mathematics, we first need to know some little tricks to be able to add all those small partitions that are integral to our area. And for that, we're going to be using the sigma notation. This is what the sigma notation looks like. It's this Greek letter sigma that we're using, all right? In the Greek alphabet, this is the capital letter sigma. All right, what is sigma notation used for? Well, sigma notation is used to denote the sum of the first n terms in a sequence, all right? So the sum of n terms in a sequence. All right, and how do I determine these terms in a sequence? All right, well, this formula is the one that is going to tell me how do these terms look like. All right, and it's going to tell me how do I even know where to start. Well, this formula here tells you to start right here. All right, this is the lower bound of summation, lower bound of summation. And when do you know how to stop? Where are you going to stop at this number? This is the upper bound of summation. And what is this letter I? This letter I is the index. This is going to tell me the index of summation. This is going to tell me where in my formula am I going to be substituting these numbers. All right, from 1, 2, 3, 4, 5, 6, all the way to the n number. And what is this? Well, this is just the ith term in a sequence. This is the fourth term in the sequence. This is the n-1 term of the sequence. This is the last number of the sequence, all right? This is the first term of the sequence. How do we determine the first term of the sequence? Well, this will tell me where to begin. This is how we're going to be doing that. So let's do an example of that. This is saying find the summation of all the terms starting at 1 and ending at 5 that follow this formula. All right, well, what are the numbers there? 1, all right, so let me plug in, this is my index of summation. Where in my formula does it say to substitute this number? Oh, well, right here, it's just an I, all right. Well, on the first one, it's gonna be 1, all right. Then I go to the next number, a 2. Where do I substitute this 2? Where there was an I. Oh, well, there's a 2, a 3, a 4, a 5, all right. That's where we stop. This is my upper bound of summation. Well, the total sum of this is equal to 15, and I just added the first 5 terms of this sequence.